Now let's look at solution for this question based on Einstein's photoelectric equation. Here it is given a photosensitive surface with work function of 1.98 electron volts. When a radiation of a wavelength some 4.4 into 10 power minus 7 meters is incident on that photosensitive surface, the possible maximum kinetic energy of photoelectrons is asked. Here, by Einstein's photoelectric equation, we know that the energy of an incident photon is equal to the sum of the work function of the given metal surface and the maximum kinetic energy of the photoelectron so released. So that we express as E, the energy of incident photon, is equal to W, the work function of the photosensitive surface, plus the maximum kinetic energy of the photoelectron so released. And of course, as you know, the Einstein's photoelectric equation is defined and valid for the total transfer of energy of the incident photon to the electron that is bounded in the metal surface, and as it is released, so we get the maximum kinetic energy in the equation. That reason was well explained in our synopsis. And here, therefore, this incident wavelength is being known. I write in the form of wavelength E equal to hc by lambda is equal to W plus the maximum kinetic energy of photoelectrons. Here, it's given the work function in electron volts, and if we go and maximum kinetic energy of photoelectrons in the options is also in electron volts. Therefore, let us simply apply a logical relation to solve this numerical in a quick time, and for that let's write this equation as 12,400. In the previous numerical I have explained about this. The H value we take as 4.14 into 10 power minus 15 electron volt seconds, and C value 3 into 10 power 18 angstrom units per second. So by substitution of that, we can say 12,400 by lambda in angstrom units. This time the wavelength of incident radiation we have to substitute in angstrom units, so that we get all this energy in electron volts, and this is equal to